Assalamu alaikum and Bismillahir Rahmanir Rahim. So today is first lecture of week 12 and we are starting with chapter number 14. So chapter number 14 it consists of two main modules. One is feedback in electronic circuits and the other is oscillators. These two modules are interrelated as we will be able to see later inshallah. So the first module is feedback in electronic circuits. You are already familiar with the theory of feedback from your control and signal courses. So in this course we discuss the feedback in the context of electronic circuits. So we first start with the basic theory of feedback, and then the types of feedback in electronic circuits. And before discussing the types of feedback in electronic circuits, we also discuss the motivation. What is the advantage of having feedback in electronic circuits? And furthermore, we will also discuss an example of an electronic circuit with feedback. Our discussion is primarily on feedback in amplifier circuits. So we will see what are the different issues that have to be considered in amplifier circuits with feedback. So here you can see a general block diagram for a system with feedback. So here the X is the input, Y is the output, and E is the error signal in terminology of control theory, which is equal to X minus beta Y. So generally speaking, A will be the gain of the amplifier without feedback, and beta is the gain of the feedback path. X, Y and E can either be a voltage or current. X and E will always be the same. That is, if X is a voltage, E will be a voltage, and if X is a current, E will be a current. And the same goes for the output of the feedback path. So if the output of the feedback path is a voltage, both X and E will be voltages. And if output of the feedback path is current, then it means that X and E are also currents, because you can have addition of subtraction only when you are dealing with the same quantity. You cannot subtract a current from a voltage, nor you can add a current to a voltage. However, X and Y can be different quantities. For example, X may be a voltage, Y may be a current. X may be a current, Y may be a voltage. Both X and Y may be voltages, and both X and Y may be currents. And then there is another issue. When X is a voltage and the feedback signal has to be subtracted from X, then the feedback would be in series with X, because voltages can only be added or subtracted in series. Whereas if X and E are currents, and this and so is the output of the feedback block beta, then the feedback signal has to be connected in shunt with X, because currents can only be added or subtracted in shunt. Uh, we will see this point in more detail as we discuss each type of feedback in more detail. So here is the closed loop gain of a system with feedback, which is A subscript F, and this is equal to A divided by 1 plus beta A. So A is the gain of the amplifier without feedback, and AF is the closed loop gain. So now if beta A is much larger than 1, what will happen that AF will be approximately equal to 1 over beta. This means that AF is independent of A. Now the advantage is that beta, which is the gain of the feedback path, is independent of frequency and other operating conditions. So what is the base of our claim that beta is independent of frequency? The reason is that the feedback path usually consists of network of resistors which are frequency independent. So when you have feedback in your amplifier, the closed loop gain then depends only on the value of certain resistors which are frequency independent, and furthermore their values are more or less stable, and they are more accurately known than the value of the gain of the amplifier. So you have more reliable operation of the amplifier and you have flatter gain. So here we can see that the gain with feedback is A divided by 1 plus beta A, which is approximately equal to 1 over beta. Now this gives us another information that beta has to be smaller than 1. Only then AF will be greater than 1. And if beta is smaller than 1, then A has to be much greater than 1 over beta, so that beta A is much greater than 1. So for beta A to be much greater than 1, which is our required condition, A has to be much greater than 1 over beta. And from this we can see another interesting thing, that A, which has to be much greater than 1 over beta, and 1 over beta is basically gain with feedback. So this means that A is much greater than AF, that is the gain without feedback is much greater than gain with feedback. So this is the compromise that we have to do here. In order to achieve a flat gain, that is a gain which is frequency independent in the operating frequency range, we have to compromise on the gain. An example is an op amp. Without feedback, the op amp has an extremely large gain. For example, in case of 741 op amp IC, it's between 70 to 90 dBs. But when we have feedback, the gain is considerably smaller, usually around 10 dBs. So this is the compromise that we have to make in order to achieve a flat gain. So here we have an example of feedback, and that is an inverting amplifier using op amp. So when we compare these two blocks, we can see that Vi is the input, so Vi corresponds to X. V minus is the input to the block A, so V minus corresponds to E, and V naught is the output, which corresponds to Y. So this is the correspondence between these two figures. And now we can analyze the inverting amplifier based on the op amp in more detail, so that we derive the equation of V minus, that is the input voltage, that is the voltage at the inverting input of the op amp, in terms of Vi and V naught, so that we can see that we indeed have feedback from the output. And we can see this feedback from the output just by looking at the figure, as the inverting terminal of the op amp, that is the inverting input of the op amp, is connected to the output through RF. And when we derive the equation of this voltage at the inverting input of the op amp, we will see that it also contains a term which is a function of V naught. So how do we derive V minus? So our strategy would be using superposition principle. So now we can consider V minus as sum of two voltages. One is Vi minus, which is V minus due to the input voltage Vi, and the second term will be V naught minus, which is V minus due to the output V naught, and this second term represents the feedback. So first we derive Vi V minus, that is Vi minus, which is V minus due to the input Vi. So as you are familiar with superposition principle, in superposition we take a voltage as sum of voltages due to all sources one by one. So what we do when we are considering a specific source, we make all the other sources equal to 0. That is, we make all the other voltages as short circuit and all the other current sources as open circuits. So in this circuit we have two voltages which we are considering. One is Vi and the other is V naught as sources for V minus. So now we are considering the input voltage Vi. So for this purpose we will make V naught equal to 0, that is, we will replace V naught by ground, and this is what you can see in this figure. So V naught is grounded, and now we have to find V minus due to Vi alone. So as the inverting input of the op amp is effectively an open circuit, and the same goes for the non-inverting input as well, because we know that the input impedance of op amp is very high. It's in order of mega ohms, so we can consider these inputs to be open circuit. So this now simply becomes a voltage divider problem. We simply have Vi, and then we have connection between Vi and ground through a series combination of R and RF. So R and RF are simply in series, and using the simple voltage divider law we can find the expression for Vi minus, which is RF divided by RF plus R into Vi. So this term basically is the contribution of input to V minus, and as usually the RF will be much larger than R. The term RF divided by R plus RF will be approximately equal to 1. So Vi minus, that is the contribution of Vi to V minus, will be approximately equal to Vi. So once we have found the expression for Vi minus, that is contribution of Vi to V minus, we can proceed to find the contribution of V naught to V minus, which represents the feedback term. So here we have V naught minus, which is V minus due to V naught, and this can be found by making Vi equal to 0, that is by grounding Vi. So as the Vi is a voltage source, so in superposition we will replace all the voltage sources by ground, with the exception of the source that we are considering at a given time. Now this again is a voltage divider problem, and so V naught minus is simply R divided by R plus RF into V naught. So now we can see that we have a feedback from output to the input. This term V naught minus is basically beta V naught. This is the term which contributes to the input coming from the output through the feedback path. So now we can combine these two terms, Vi minus and V naught minus, to find the complete expression for V minus. And this is what you can see here. So V minus is sum of the input and the feedback from the output. And as you can see here, where RF divided by R plus RF is approximately equal to 1, as RF is much larger than R. So V minus is then approximately equal to input plus certain constant multiplied by output. So this constant is now our beta. So we can simply say that V minus, which corresponds to E, is equal to X minus beta Y. So let's see this point in more detail, and you can see that the gain of the feedback path is determined by resistors R and RF. So now we write this equation in standard form, that is V minus, which is basically E of our standard block diagram for a system with feedback, is equal to the input X minus beta times Y. So in this case, beta is now minus R divided by R plus RF, and AF, which is the gain with feedback or the closed loop gain, is 1 over beta, and this is approximately equal to minus RF by R. This is the equation that we already derived when we were discussing op amp circuits. So this is an approximate analysis, but even if you do exact analysis with some adjustment, that is, then you make some substitution, so then you can have exact mapping between EXY on one hand and V naught Vi and V minus multiplied by certain constant on the other hand. So other examples of feedback in electronic circuits is majority of op amp circuits. So in fact all the op amp circuits where you don't go into saturation region, they have feedback. Without feedback you cannot avoid saturation in op amp circuits. And even in some circuits which have saturation you have feedback. The example is the Schmitt trigger. The BJT and FET voltage follower circuits, they have feedback, as the voltage at the emitter terminal, which is the output, is acting like a feedback signal, because the active voltage on the input side is VBE, and VBE is equal to VB minus VE, and VB is the input voltage whereas VE is the output voltage. So there you have feedback from output to input. And then you have feedback biasing like collector feedback biasing in BJT and drain feedback biasing in FET. Another example is Miller effect, where the output voltage affects the capacitance on the input side, which then affects the frequency response of the amplifier circuit. So this is also an effect which can be considered as feedback from output to input. And oscillators are mostly designed by, using feedback. So these are certain examples of feedback in electronic circuits, and PLL is also one of them. In PLL you also have feedback from output to the input. PLL, that is the phase lock loop that we studied earlier. So what are the different types of feedback in electronic circuits? Or we can rephrase our question as how we can classify feedbacks in electronic circuits. So we have four types of feedback. When we classify the feedbacks in terms of output and the type of connection that feedback has with the input. So the first one is voltage series feedback. In this the output is voltage and feedback is connected in series with the input. The second is voltage shunt feedback. Here the output is voltage whereas the feedback is connected in parallel to the input or in shunt to the input. The third one is the current series feedback. In this the output is current whereas the feedback path is in series with the input. And finally we have the current shunt feedback, in which the output is a current and the feedback path is connected in parallel to the input path or in shunt to the input path. So if you look at these four types, the first word represent the type of the output. So if it is a voltage feedback, then the output is voltage. If it is a current feedback, then the output is a current. Whereas the second half of the type of feedback represent the type of connection that feedback path has with input. So if you have series feedback, it means that the feedback path is in series with the input. If we have shunt feedback, then it means that we have parallel connection of the feedback path to the input path. So let's see the block diagram of the voltage series feedback. So here we have the block diagram of the voltage series feedback. So you can see here the output is a voltage V0 and feedback is in series with the input. So now we know that if there are two electrical quantities and they are added or subtracted from each other and they are connected in series, then they have to be voltages, because when you connect two components or two circuits in series, their voltages are added, and if you connect them in shunt, then their currents are added, not their voltages. So if we have series feedback, that is if the feedback path is in series with input, then feedback has to be in form of a voltage, and if feedback is in form of voltage, then input also has to be a voltage, because you can only add same quantities. You can only add or subtract voltages, or you can only add or subtract currents. So let's have some more discussion on voltage series feedback. So V0 will be equal to A times Vi, so this means that A is equal to V0 by Vi. So here A is a dimensionless quantity representing the gain of the amplifier without feedback. And similarly beta is Vf or V0, a dimensionless quantity representing the gain of the feedback path, and beta A is dimensionless. Another important point, beta A will always be dimensionless, because if you look at the equation for closed loop gain, AF is equal to A divided by 1 plus beta A. Now this equation will be true for all feedback types, as we can see later. So you can only add quantities of the same dimension. So if you have something, if you have a term 1 plus beta A, this means that beta A has to be dimensionless. And we will see later inshallah that beta A is dimensionless in all the four types of feedback. So this is the voltage series feedback, and this is how the feedback path is connected to the input. So the feedback path is connected in such a manner that Vi is equal to the difference of Vs and Vf. That is, Vi should be equal to Vs minus Vf. So then we connect, for this purpose we connect Vf with opposite polarity. So normally if you want to add two voltages, you connect the positive terminal of the first voltage with the negative terminal of the second voltage, and then you get sum of the voltages from the positive terminal of the second voltage and the negative terminal of the first voltage. But here we connect these voltages in opposite manner. We connect the negative terminal of Vf with negative terminal of Vs, so that Vf is subtracted from Vs. We can see this point more clearly by looking at the figure on the right side of this slide. So here is, so on the right side you have the equivalent circuit of the input stage. So you can see here negative terminal of Vf is connected with the negative terminal of Vs. Positive terminal of Vf is connected with the negative terminal of Vi, whereas positive terminal of Vs is connected with the positive terminal of the Vi. So if you compare these two figures, you can see that the diagram on the right side is indeed correct diagram, showing the connection of voltages on the input side. So now if we do the loop analysis on the figure on the right side, we can see clearly that Vs is equal to Vi plus Vf. The loop equation will be Vs minus Vi minus Vf is equal to 0. So which is then Vs is equal to Vi plus Vf, and this means that Vi is equal to Vs minus Vf. So here we can now see clearly that Vf is indeed subtracted from Vs, and Vi is equal to Vs minus Vf, and this is what we were trying to achieve, because we want to have negative feedback, that is the feedback signal should be subtracted from the input. So here you have more detailed derivation. So Vi is equal to Vs minus Vf, and then we put the expression for Vf, which is beta times V naught. So Vi is equal to Vs minus beta times V naught. Then we put the expression for V naught. So V naught is equal to A times Vi, which means that beta times V naught will be equal to beta A Vi. So this means that Vi will be equal to, so Vi will be equal to Vs minus beta A Vi, and then we bring the term minus beta A Vi on the left hand side, so we get Vi plus beta A into Vi is equal to Vs, or Vi into 1 plus beta A is equal to Vs. And finally we get the expression for Vi in terms of Vs. So Vi is equal to Vs divided by 1 plus beta A. So this is one of the main equations, so which I have highlighted in this uh, blue purple color that you can see on this slide. So Vi is equal to Vs divided by 1 plus beta A. And then the next step is simple. V naught is simply A times Vi. So V naught is then A divided by 1 plus beta A into Vs. So then now the gain with feedback, which we define as ratio of V naught, the output, to the ratio of the source voltage, the input voltage Vs. So the gain with feedback will be defined as ratio of V naught over Vs, because Vs is our actual input, Vs is our X. So let's remind ourselves. So in this case Vs is X, Vi is E, and V naught is Y. So the gain with feedback, which is Y over X, will be equal to V naught over Vs, and that will be A divided by 1 plus beta A. So hence we have proved that it is indeed behaving like a system with feedback loop, and the gain with feedback is simply A divided by 1 plus beta A, which is the standard equation for closed loop gain of systems with feedback. So here you can see the correspondence between voltage series feedback circuits and general system with feedback. So here Vs corresponds to X, Vi corresponds to E, and V naught corresponds to Y. So this concludes our discussion for today. So what next? So in the next lecture, inshallah, we will discuss the other three feedback types, that is voltage shunt feedback, current series feedback, and current shunt feedback. And if time permitted, also feedback example. Otherwise we will discuss the feedback example in the lecture after the next lecture. So that's it for today. So good luck and Khuda Hafiz.